thanks everyone for coming. This will be our last formal discussion hour talk of the semester. Week after next, we'll do a little AGU prep. I'll make an announcement about that at the end. But for now, I am pleased to introduce Nicole. Nicole Ferrie is a PhD candidate interested in utilizing geochemical behavior to research seismologic processes and paleoclimate reconstruction. Her research focuses on using boron adsorption as a fluid tracer in shallow subduction complexes and as a proxy for paleoatmospheric CO2 reconstruction in paleocells. So Nicole, go ahead and take it away.
Okay, awesome. Thank you guys for being here. I'm sorry I couldn't be there in the room. I'm in Houston at Rice doing lab work, and I had to get it in before AGU. So that's why I'm virtual, but I appreciate everyone coming. Thank you guys. And so my research focuses on using geochemical insights on boron adsorption on clay surfaces and how these insights can be helpful in understanding Earth systems. So before getting into the Earth systems, I wanted to get a very basic understanding of boron adsorption onto clay surfaces. So boron adsorption onto clay minerals is pH, temperature, and lithology dependent. And here I have three figures indicating all those dependencies. So on the y-axis is the amount of boron adsorbed. The higher the number, that means the more boron that's adsorbing onto the clays. And the lower the number, the less boron that's adsorbing. And then on the x-axis for all these figures is pH. And so here looking at the pH dependence, we see a characteristic bell curve of boron adsorption, with boron adsorption reaching a peak at intermediate pHs, which are typical of natural systems. And then at lower and higher pHs, boron adsorption drops off by quite a bit. In the middle here, we have temperature. So here I have boron adsorption at 25 degrees Celsius and then boron adsorption at 75 degrees Celsius. Boron adsorption decreases with increasing temperatures. And then with lithology here, I have boron adsorption on two different clay minerals. One is illite, which is the black here, and then the other is chlorite, which is the purple here. Illite adsorbs more boron than chlorite does. And so the fact that boron adsorption onto clay minerals is pH, temperature, and lithology dependent helps us understand geologic systems, as well as it can be applied to environmental remediation. And here I have a list of how boron adsorption on clay minerals can be used. One of these processes is the desalination of drinking water. So when we desalinate seawater for drinking, there is 5 ppm of boron in seawater, which is too high of a level for human consumption. So what we can do is we can put clay into the seawater to help remove boron. Another useful application of boron adsorption onto clay minerals is wastewater treatment. Boron is a byproduct of a lot of industrial systems, and the wastewater needs to be treated and boron removed before the wastewater can be released back into the natural environment, which is again where boron adsorption onto clay minerals can be helpful to remove this boron from the wastewater. Additionally, understanding how boron adsorbs onto clay minerals can be important for crop vitality. Boron is an essential nutrient for plant life, but in too high of concentrations, boron can actually kill plants. And at too low concentrations, the plants can die from lack of boron. And clays are a very large part of soil systems. So understanding how boron is taken up by clays and how much boron is taken up helps us understand how much boron is left over for the plants to actually consume. And it helps us understand if we need to add more boron to the soils or take away boron. So we hit that sweet spot where crops can thrive. Additionally, boron can help us improve paleo-CO2 reconstruction using paleosols. That is one part of my research, but I'm not going to talk about that as much today. What I'm mostly going to be talking about is how boron adsorption onto clays can help us better understand geochemical cycles and fluid release and migration pathways in shallow subduction systems. So I want to talk about now how fluid release and migration pathways in these subduction systems is actually important. So within subduction systems, we have a hydrologic system where fluid-rich sediment enters into the trench and fluid is either released back up onto the surface into the sea, or it's subducted down into the subarc. Now, whether these fluids, which have chemicals in them, are released back up into the Earth's surface or is subducted down helps us understand how geochemical cycles work. Where they are released, whether it's at the volcanic arc or they're released back into the sea. Additionally, hydrologic systems are very important for our understanding in seismogenesis. Fluid release can contribute to regions of high pore fluid pressure, which impacts fault mechanics and earthquake generation. Now, how fluid release and migration actually works in these subduction complexes is illustrated here in this figure. So on the incoming plate, we have fluid-rich phyllosilicate sediments. And as this fluid-rich phyllosilicate sediment, which I have here as just this package with pore spaces with fluid and then other just little sediment in it, as it enters into the trench and is subducted down, it is subjected to increased tectonic stress and pressure. This causes consolidation of sediment and a reduction of porosity, which I have shown here. And the reduction of porosity leads to the release of pore fluid. Now, most porosity reduction occurs within 3 to 4 kilometers of the trench. Now, we can actually understand where the fluid is being released and these migration pathways through the use of boron, which I'm going to illustrate here. So say we have the same package of sediment, and this package of sediment has pore spaces. These pore spaces are filled with fluid. Now, the fluid composition is the same as seawater, and so that means that it has 5 ppm boron in it. Some of that boron is adsorbed to the clay surfaces, and some of that boron is sitting in the pore space in the fluid. Now, as that package of sediment subducts down and is subjected to increasing temperatures and pressure, some of the boron is going to desorb from the surface of clays into the pore fluid as a function of temperature. And then as that sediment is compacted and that fluid is released, those fluids will travel up through pre-existing fissures and cracks in the subduction zone out to the sea floor. We can then sample the fluid that's coming out of the subduction zone and look at the boron concentration. We can then link the boron concentration to a certain temperature and use a geothermal gradient to link that temperature to a depth at which this fluid is being released, or a region of where this fluid is being released. Now, the number that we use to distinguish where exactly, or the temperature, the concentration that the boron is to the temperature is through the distribution coefficient, or KD, which I have in this figure here. So KD is the amount of adsorbed boron versus boron in solution. A higher KD means that more boron is adsorbed to the clay surfaces, whereas a lower KD means more boron is in solution. At lower temperatures, KD is higher, meaning more boron is adsorbed to clays, and then at higher temperatures, KD decreases, which means that boron is desorbing. Now, this distribution coefficient, again, is what helps us link boron to a temperature, and then that temperature we can then link to a depth of fluid release. The issue is that oftentimes the distribution coefficient is likely poorly constrained. And that is because oftentimes when people figure out this distribution coefficient, they only figure out how boron, how the distribution coefficient of boron changes as a function of temperature, but negate lithology and pH, which are equally as important as temperature in figuring out the distribution coefficient. Now, here I have illustrated why. So here's the same figure that we saw on the second slide with the amount of boron adsorbed on the y-axis and then pH on the x-axis. However, this time in the red box, I have the pHs that are typical of subduction zone systems, and that's 7.5 to 8.1. This is a range in which the amount of boron adsorbed changes by quite a bit. And so depending on the pH that you have in the subduction system, your distribution coefficient is going to change by quite a bit. Additionally, here I have lithology. So clay is the predominant carrier of boron into subduction systems. And here I have the amount of clay on the y-axis in weight %, and then subduction zones around the world on the x-axis. So Tohoku, Barbados, and Hikurangi have very high clay content, whereas Niankai, Cascadia, and Costa Rica have a lot lower clay content. The distribution coefficient of boron is going to change with clay content. And then lastly, I have temperature. And most boron desorption occurs by 160 C. So boron adsorption can be used as a fluid tracer from 0 to 160 C. So if you only consider temperature but don't consider lithology and pH, you could have an incorrect distribution coefficient, which means that you could be incorrectly sourcing these fluids using boron. So what we want to do is we want to ask the questions, how does the distribution coefficient vary among different subduction zones as a function of lithology, pH, and temperature? And once we know that, is there a systematic way to predict the boron distribution coefficient in different subduction zones without experimental work? Figuring out the distribution coefficient is costly, time-consuming, and not everyone has access to these drill core samples. So in order to do this, we need to understand exactly how boron adsorption or distribution coefficient is affected by lithology, pH, and temperature. And in order to do this, we break down these phyllosilicates or clays into their most basic form. So here I have 3 phyllosilicates or clays that are common in subduction systems: illite, kaolinite, and chlorite. And then here I have in these little blocks their most basic structure. So clays are mostly composed of silica tetrahedra and aluminum octahedra. And the relationship of silica tetrahedra to aluminum octahedra changes with different clays, but always remains constant within each clay. So that means that illite, the structure of illite is different than the structure of kaolinite, but illite will always have this structure. So now what we want to do is we want to look at how boron adsorbs to silica tetrahedra versus aluminum octahedra, basically separating the 2 basic components of these clays. And here I have a 2 figures illustrating this. So on the left-hand side, I have how KD, or the distribution coefficient, changes as a function of temperature. And then here I have how the distribution coefficient changes as a function of pH. Looking here at the left-hand side, we see that corundum, which is 100% aluminum oxide, adsorbs the most amount of boron, whereas in the green here, there's just 1 point for temperature. But silica oxide, or silica tetrahedra, adsorbs almost no boron. And then in the middle, which is purple, are the clays, which are composed of this aluminum octahedra and silica tetrahedra. And then here we see the same relationship with KD versus pH, where the red line is the red dots are aluminum octahedra, and they adsorb the most amount of boron. The silica oxide adsorbs no boron, and then the clays fall somewhere in the middle, which leads us to believe that boron adsorbs to only aluminum oxide sites and not the silica oxide sites within the clays. Now, why is that? Well, there's 2 reasons why that is. And one is due to the fact that boron speciation is pH dependent, and another is due to the surface charge of aluminum octahedra and silica tetrahedra. So first, looking at boron speciation as a function of pH, I have this figure. And on the y-axis is the abundance of boron species. And then on the x-axis, I have pH. Now, at low pHs, boron is predominantly in the form of boric acid, which doesn't adsorb as it's a neutral compound, or adsorbs in a very low amount compared to over here, which is borate. So borate occurs at higher pHs and is a negatively charged anion, which is predominantly adsorbing to the surface of clays. In subduction systems, we have a pH of 7.5 to 8.1 typically, so we have some amount of borate and mostly boric acid. Now, looking over here at surface charge, I have the point of 0 charge for silica oxide and aluminum oxide. Now, the point of 0 charge is the pH at which you have a surface, and the amount of surface sites that are positive and the amount of surface sites that are negative are exactly equal, so the surface has a neutral charge. At a pH below the point of 0 charge, the surface is going to be predominantly positive, and then at a pH above the point of 0 charge, the surface is going to be predominantly negative. Now, within the typical range of pHs of subduction zones from 7.5 to 8.1, we see that silica oxide, which is in the red, is going to be predominantly negatively charged, and aluminum oxide, which is here in the blue, is going to be predominantly positively charged, which leads to this trend, which is where, I have a figure here of silica oxide and aluminum oxide, and then I have how boron in solution is going to interact with the silica oxide surfaces and the aluminum oxide surfaces. So at intermediate pHs, which we see in subduction zones, for silica oxide, the boric acid isn't going to adsorb, and the negatively charged borate is going to be repelled from the surface of the silica oxide. But looking at aluminum oxide, we see that, again, boric acid won't adsorb, but the negatively charged borate will be attracted to the positively charged aluminum oxide surface sites, which leads to boron only adsorbing to aluminum oxide sites in subduction zone systems. So we believe then that we can predict the amount of boron adsorption onto these clays if we know the percentage of the surface that's aluminum oxide versus silica oxide. So here I have 4 materials. I have these 3 clays, which are predominant in subduction zone systems: the illite, kaolinite, and chlorite, and then corundum. Corundum is 100% aluminum oxide, so all the sites are going to be aluminum oxide. For illite, it's composed of silica tetrahedra, aluminum octahedra, and then silica tetrahedra. 28% of the surface of illite is aluminum oxide, whereas 72% of the site is silica oxides. The surface is silica oxide. kaolinite is 19%, and then chlorite is 17%. So what we can do is we can do boron adsorption experiments where we see how much boron adsorbs to 100% aluminum oxide, and then actually scale down the amount of adsorption that we see on corundum by the percentage of aluminum oxide available on the surface for the different clays, for illite, kaolinite, and chlorite. And here I show this with the amount of boron adsorbed on the y-axis and then pH on the x-axis. The red is corundum, which is 100% aluminum oxide and has the highest amount of adsorption. The black, blue, and purple are illite, chlorite, and kaolinite. And we can see that this scaling factor works where the amount of boron adsorption on corundum is scaled down by the aluminum oxide mole fraction and equals the amount of boron adsorption that you would get for these three N-member clays. Now, this work was previously done by Bassett in 1977, and we would like to extend this work to natural sediment clays or natural marine clays, which contain a lot more than just these phyllosilicates. However, we hypothesize that the distribution coefficient of marine clays at various pH, temperature, and lithology can be predicted based on the number of aluminum oxide sites on the surface of phyllosilicates within a natural clay. Meaning that if we have a natural marine clay and it's composed of feldspars, organic matter, quartz, calcite, and phyllosilicates, nothing matters but the phyllosilicates, specifically the percentage of aluminum oxide on the phyllosilicates within the natural clay. And the reason why that is that feldspars are predominantly composed of silica and have very little aluminum oxide sites. So the amount of boron adsorption onto feldspar can be considered negligible. Organic matter does adsorb boron, but organic matter is typically available at very low percents compared to phyllosilicates. So that adsorption of boron can be considered negligible. Quartz does not adsorb boron because it's made of silica oxide. And then calcite adsorbs very little boron compared to phyllosilicates, and is also typically at much lower concentrations, which just again leaves us with the phyllosilicates. So then we believe that we can do an N-member mixing model to find out the percentage of aluminum oxide available on the surface of a natural clay. And here I have illustrated how we do that. So say we have a melange shell here, which is a natural subduction zone clay, and it's composed of quartz, feldspar, illite, and chlorite. We look at the X-ray diffraction, or the weight percent of minerals inside this clay, and we figure out that 21% is feldspar, 39% is quartz, and 40% is clay. We don't care about the feldspar and the quartz because that doesn't absorb any boron, but we do care about the 40% clay. Out of that 40% clay, it's composed of 76% illite and 4% chlorite. Now, illite and chlorite have their own aluminum oxide percentage that's available on the surface. So what we can do is we can multiply the amount of illite present in the sample by its aluminum oxide surface percentage, and then do the same for chlorite and multiply that by the amount of clay to get the overall aluminum oxide percentage available on the surface of a natural clay. We can then apply the same model where we basically scale down the amount of boron adsorption that we see on pure aluminum oxide by the aluminum oxide percentage available on the natural clay, which we found through the N-member mixing model. Now, I have applied this model to several different subduction zone clays with different lithology. Here I have the same figure that we saw earlier, where we have the weight percent of clay in the bulk sample on the y-axis and different subduction zones on the x-axis. The red stars are the samples that I have done these boron adsorption experiments on thus far. Hikurangi has a higher clay content than Nankai does. Now, here I have the results, and I know this figure is complicated, so I'm going to walk you through it. On the y-axis, we have the distribution coefficient, where the higher the distribution coefficient, the more boron that's adsorbing, and the lower the distribution coefficient, the less boron that's adsorbing. And on the x-axis, we have pH. In the black, we have boron adsorption results on corundum, which is this 100% aluminum oxide. And then in the green and the yellow points are boron adsorption results from Nankai. And then in the orange, I have boron adsorption results from Hikurangi. In the red box here, we have the pHs that are typical of subduction zones. And then the line is our model application. So our model application is where I took the amount of boron adsorption on corundum, and then I scaled it down by 10% and 11%, which is the result, which is the aluminum oxide percentage on the surface that we got from the N-member mixing model, and saw how well it fit over the points. And so a couple of things to note here is that on just the Nankai material, the model works fairly well with the model falling directly over the experimental results. And then additionally, in the box where pHs are typical, the distribution coefficient of Hikaringi is quite different than the distribution coefficient in Nankai, indicating that based on lithology alone, the distribution coefficient does change, not even considering differences in temperature. And so going back to the original two questions we asked, how does the distribution coefficient vary among different subduction zones as a function of lithology, pH, and temperature? The answer is that the distribution coefficient does vary with different lithology and different subduction zones and different pHs. And with temperature, we are still trying to answer that question through experiments. And then, is there a systematic way to predict the boron distribution coefficient in subduction zones without experimental work? So far, we'd like to say yes, based on this preliminary evidence, but more experiments are needed to say that with confidence on different subduction zone material at different temperatures, which leads me to my future work. So in the future, we would like to continue to do boron distribution coefficients on different lithologies at different pHs, and then expand our model to include temperature, and then take this improved distribution coefficient and plug it into a subduction zone model that also simulates heating and compaction to get a model that would represent fluid release, that would represent what the boron distribution coefficient would be with fluid release at different depths. That being said, I do want to take a step back from the subduction zone work and point out that this model is not only applicable to geochemical cycles and fluid release migration pathways, but also all of these other things listed. Thank you, and I'll take any questions now. Cool. Thanks, guys.
Any questions? Alice?
So if it all depends on like the surface area of the aluminium oxide, I'm not a geochemist. I didn't go editing the geochemistry class, so maybe I can totally misunderstand everything. If it all depends on the surface area of the aluminium oxide, does that change as the sediment gets squished as it goes down? Like, does the surface area of the whole thing get smaller too?
Yeah, so the surface area will change, but essentially, so something that I didn't, oh no. Oh, okay, I'll just do that. So something that I didn't mention is that our results are actually normalized for surface area. And so that's where this meter squared is. So basically there's this process called Braunauer, Emmett, and Teller surface area analysis where you can put your material into this machine and it'll give you the surface area. And then you can basically normalize your distribution coefficient for surface area, which is taking the effect of surface area out of your distribution coefficient. So yes, your surface area will change as compaction occurs during subduction, but we can remove that process by normalizing for surface area.
Thank you very much.
Yeah.
I have a question. Great talk, Nicole. This is interesting. I may have just missed this in the intro, but so you, let's say, drill a borehole in some subduction system, you get your lithology, so you can do what you just did. Maybe you make some inference about temperature. Where do you get information about pH? Like, how do you determine that to constrain?
Oh, yeah. So you can determine that through alkalinity. And so a lot of times the alkalinity is reported, and there's an equation that you can use where you can go from alkalinity back to pH. And so like on the ship, they'll report that, yeah.
Okay, thanks.
There you go. Could you explain a little bit more on like what are your thoughts on the differences between the two subduction zones that you mentioned? What is like causing the difference in a coefficient?
What's causing the in the distribution coefficient? So right now, all these adsorption experiments were only done at one temperature, so 25 degrees C or like room temperature is what I've been doing these experiments at so far. And so we're really looking at how pH and lithology affect the distribution coefficient. And the pH affects the distribution coefficient because boron adsorption changes over different pHs, which I have here essentially at different pHs. Well, okay, so did you did you understand like the pH dependence of boron speciation?
Yeah, I guess not like the theoretical side, but more like what exactly is the difference between the two subduction zones that you think could explain what's happening?
Yeah. It's lithology. So
Okay.
basically, Haringey has a ton of montmorillonite in it, and then Nankai has a lot of illite and chlorite. Illite and chlorite have a much higher aluminum oxide surface percentage than montmorillonite does, we believe. And we're doing this process called XPS. And basically what the process is that you can put your material into this machine, and then it'll give you back the chemistry of just the surface. So it'll tell you the percentage of aluminum that's just on the surface of these clays. And so that's another step we're using to corroborate it. But we believe that montmorillonite would have a much lower aluminum oxide content than chlorite and illite, which has also been proved through experimental results from Bassett, which is, I have a slide of here. The difference is really small just because corundum absorbs so much, but the black is illite, and oh yeah, I don't have montmorillonite. Never mind. But we believe that montmorillonite would fall more around the 5 to 6% range down here. So it have
Maybe, yeah, thanks. Maybe like a follow-up question. Have you tried like testing a long strike samples? Is it gonna be very different along the subduction zone, or is it gonna be more or less uniform?
Yeah, so I haven't done any adsorption experiments along strike yet, but I have looked at the lithology along strike. So for example, for Nankai, these are two different drill cores, and they're kind of like a long strike of the subduction zone, and they have a pretty similar clay percentage. I would really need to dig more into the XRD, so look at the different phyllosilicates within the clay to answer that question. But for Nankai, based on just this figure alone, the clay content, I would say there is not as much variation within subduction zones as there is between subduction zones. But yeah, I would need to look deeper in the mineralogy to answer that question. That being said, though, for Cascadia, these are also two different sites that are along strike, and they do differ in clay percentage. So I guess I would take that answer back. I would say that it's dependent on the subduction zone. For Nankai, I would initially say no, it would not vary a lot along strike. And then for Cascadia, I would say that yes, there would be maybe a notable variation along strike.
Yeah.
I guess I have one. So you mentioned like these other applications,
Yeah.
so wastewater treatment, and I mean, are you looking to, I guess, apply that to any of these? I know like there's the
Mhm.
big talk, especially in Texas, about like the largest like wastewater pure water purification plant is being built in like Houston right now. And
Yeah.
then there's a desalination plant that may be built. So like local applications here.
So yeah, no, that is a great question. And if I had more time, I definitely would want to apply it to wastewater system, wastewater treatment or desalination. But really what my focus is right now for my PhD is this paleo CO2 reconstruction, and then the fluid release and migration pathways, as well as the geochemical cycles. That being said, there's like the first aspect, right, which is the improved distribution coefficient. And the improved distribution coefficient is what you can apply to all of those other things that I listed. And so basically what we want to do is we want to publish a paper in like American Chemical Society or something like that with just this model, not applied to subduction zones, in the hope that it will reach communities who do this kind of work, and then later on do more specific subduction zone modeling, and then put it in like G cubed or something like that. So the answer is, am I going to do anything directly with these? No. But do I hope other people do with this model? Yes. And if I continue this work in like a postdoc or something, then I think it would be interesting to do like these sort of applications. But within my PhD, probably not.
Yeah, go for it.
Can I ask about your paleo CO2 reconstruction then? I was curious about that, like what type of work are you planning to do with paleo solids?
Yeah. So basically with the paleo CO2 reconstruction, I wish I had supplementary slides right now. But basically, so it's a new proxy that hasn't been created yet, actually using boron as a way to improve this paleo CO2 reconstruction. And the idea is that similar to subduction zones, soils have these pore spaces within them. And it's composed of gas and water. And basically, some of the CO2 in the pore spaces is from respiration from plants, and then some of it is from respiration from the atmosphere. And the idea is that these carbonates that are within soils have a concentration isotopic carbon composition that allows you to look at what the CO2 concentration was in the pore spaces at the time that the soil was existing on the surface. So basically, like, you have these soils at the surface, they have a certain amount of CO2 from plant life, like from respiration, and then from the atmosphere. Carbonates, which are forming in the soil, track that concentration, and then those soils are buried, become a paleosol. Then you can pull out the carbonate, do some tests on it, and then say, like, oh, I know that the carbon concentration was this, like there was this much ppm in the soil. But you can't directly link that back to atmospheric CO2 yet, because it's a mixture of respiration and CO2 from the atmosphere. So you need to be able to separate how much CO2 is coming from respiration and then how much CO2 is coming from the atmosphere. And that's where boron can come in, because basically what it does is you can it like helps you quantify the amount of CO2 that's coming from plant respiration, and then the amount of CO2 that's coming from the actual atmosphere. Because right now there's a number that's used that's just one size fits all and doesn't consider the fact that respiration changes throughout time.
Oh, thank you.
Yeah. Yeah, and that is linked to the pH dependence. And so what we mostly want to focus on is how the pH, how boron adsorption changes as a function of pH onto clays, and then we want to take out the temperature effect. So yeah, so it's nice that boron responds to all of these different parameters, but sometimes it's kind of frustrating when you just want to look at one and then have to consider how it's affected by all of these other things.
Thank you.
Yeah. Yes.
Anyone else? Anyone online? Yes, go Alice.
What lab stuff are you doing right now?
Yeah, so I am, like, right now I am in Houston at Rice, and I'm doing ICP-MS because basically when you do these boron adsorption experiments, you take the clay and then you powder it. Like, you take the clay from the drill core, powder it, you take all the boron off that's already adsorbed on the surface. So the surface is completely clean, all the sites are clear, there's no boron anywhere. And then you adjust the pH, spike it with an artificial amount of boron, let the experiments hang out, let the boron absorb, and then you take out some fluid, put it in the ICP-MS, and then it will tell you how much boron is in the fluid. So you can say, okay, like, if I put in 5 ppm of boron initially, let the experiment react, and now I only have 3 ppm of boron in the solution, then I know that 2 ppm absorbed. And so that's what this ICP-MS round will tell me, is basically how much boron adsorption occurred on different materials.
Thank you.
Yeah. Yeah, and that was because it's basically for the preliminary results that I showed here, there's a lot of noise that you can see for the corundum and both the Nankai, and that's because we think that the characteristics of the surface change every time you prep the clay. And so we are now just doing big batches of material, like prepping one batch at a time, characterizing it, and then just using that for boron adsorption experiments. So theoretically, or what I hope is going to happen, and I'm going to see from these results, is that the trends are going to be a lot cleaner and there's going to be a lot less noise.
Anyone else? Anybody else? No? Okay, so we'll thank Nicole one more time.
Okay, yeah. Thank you guys for coming.